if we go to something we already know and we've already factored, the thing I was talking about yesterday is those two will always multiply to be that first one. And these two always multiply to be the last one. Now, if we could factor this, chances are we would start off with, and don't write this down right now, but this is just sort of theoretical. Chances are we find one factor first. And that factor might have an x here and a number here. Now I'm going to, if I pick all the right numbers, that would be terrible, but I'm going to try to pick the wrong numbers. Let's say I say x plus 2 here is one of the factors. That would tell me, if that's an x there, then does it make sense that this would have to have a 3x squared at the front? And at the back, I would need a minus 5. And there would probably be something in the middle. This could be a possibility. It's hopeful that it's wrong, but it might be right. I hope not. We'll find out. Then, if you factored it even further, we still have this x plus 2. This might break up. And you could get a 3x and an x, and a 1 and a 5. And we notice that when it's factored completely, and maybe this one's plus and this one's minus, that the first 3 altogether still make that first one. And the last ones altogether make the last one. But this would be very hard to guess and check correctly. So we've learned some techniques. The number one thing, oh, that's a lot of color right now. I'm going to erase that. But the overall idea is that your first ones always have to multiply to get your first one. And your last ones will always have to multiply to get your last one. And that is key because once you have the factored form, I'm not going to read it quite yet, but once you have the factored form, the factors are helpful for solving, and they're helpful for solving to make something equal to 0. So we can see that if I plug in -2, this first factor would be 0. And it would not even matter what everything else is. That if I plug in -2, the whole thing will equal 0. If I can plug in the value that makes one of the factors 0, the whole thing will be 0. That's the idea of the factor theorem that you learned in grade 12. The idea of the factor theorem, though, when you now know it as steps, you might forget why those steps are there. We need to find a number that when we plug into here makes this 0. And the number that could possibly work would have to be one of the factors. And because it's one of the factors, the yellow number is giving us the hint. Because the yellow number, it might have to be an x plus 2, an x plus 1, an x minus 1, an x plus 5, an x minus 5, an x plus 10, an x minus 10. We are limited to our options for which numbers could work. And that gives us an advantage. We can start, and now we'll officially start this question. We're going to think about the minus 10. Does minus 2 actually work? Wow. Okay. And we're going to, usually I would start with 1 because it's easy mental math, and -1. But apparently I guessed right, that minus 2 actually works. If you plug in minus 2, you would get 3 times minus 2 cubed, 8, plus 4 times minus 2 squared, positive 4, minus 9 times negative 2 would be plus 18 minus 10. And sure enough, negative 24 plus 16 plus 18 minus 10 is 0. That was your factor theorem. If you find a value that makes something equal to 0, this tells you that x plus 2 is a factor. And then we can start to factor this. And what we used in grade 12 is we used our synthetic division, or you could use long division. Speaking of which, I'll show you a cartoon after this. How do we use synthetic division? Well, if we're dividing by x plus 2, we put a negative 2 outside. We bring down the 3, and then you multiply these two numbers together, and then you add. And repeat that. Multiply these two numbers together, negative 2 times negative 2, and add negative 2 times negative 5, and add. And what that will do for you is it will divide it quickly. And we can write the answer that now f of x, which we had to begin with, we've now taken out an x plus 2, and we're left with 3x squared minus 2x minus 5. And once you get a quadratic equation, well, this one, with 3x, I would start with that. Those would be my only options. And then I would think about 5 and think, should I do 5 or should I do 1? And I'll put the 5 here and the 1 here. So my outside is 3, my inside is 5. I need a negative 2, so I need negative 5 plus 3. Double check when I multiply it out that it equals to what I had to begin with. And it does. Oh, I was close. I put the 1 with the 3x, right, and the 5 with the 1. And we have factored it completely. I have the cartoon on this. Long division. So, you could use synthetic division and long division, or the factor theorem and remainder theorem to factor any x cubed graph. One of the ones that comes up quite a bit in university that isn't taught in grade 12 pre-calculus is differences of cubes and sum of cubes as something you should know as a shortcut. Now I have put together a formula sheet for this course. In 2019, if you watch those videos, they didn't have a formula sheet because it used to be that this course never had formula sheets. And it's looking like the AP course next year, for the exam, they're not allowed a formula sheet. So it's going towards the idea of, if you're learning math formulas, you need to know. So some of the things I'm going to do, even though I have certain things on your formula sheet, I'm going to show you ways to remember them, because they might not be on your university course next year, that you would have to know they would expect you to know a difference of cubes and a sum of cubes, and how you could remember how to figure them out. Okay? So now, the difference of cubes and the sum of cubes, what I do to remember these is I know that the difference one has the x minus y as the factor, and the sum one has the x plus y as the factor. So that's one thing that I do to remember. And then when I'm trying to write out the second factor, you can use the same idea of, well, if the first one's x here and x cubed here, this has to be x squared. That should make sense. And if this is a minus y cubed and I have a minus y, this would need to be plus y squared. Then, things need to always cancel out. So, for example, can you see that if you multiply that minus y times the x squared, you will get a minus yx squared. What would you need to cancel that out? You'd need a plus x squared y. So when I'm thinking about what would need to go there to cancel it out, I would need a plus xy. And sure enough, if you check other ones that you would get, for example, if I check, here I have a plus xy squared, can you see that I would need a minus xy squared to cancel it out? And so now you've just realized, okay, if I don't have my difference of cubes completely memorized, I probably can figure it out quicker than going to long division or something like that. And now, using this formula, you could factor x cubed minus 8, because 8 is a perfect cube and x is a perfect cube. It will equal x minus 2, and then you would have x squared plus 2x plus 1. And all you're doing is substituting in a 2 for the 1. And the same thing happens with the x cubed plus y cubed. You would need a negative xy for things to cancel out. Oh, and then I go and do the first and second. So the first thing we have to recognize, yes, so we can rewrite this one in here. This is going to be x minus 2, and then x squared plus 2x plus 2 squared, which would be this. For the second one, it's adding, so it's going to be a plus 3b. And again, even without using the formula, I'd probably start with going, I know this has to be a squared. And without using the formula, oh, thank you, this b squared. And without using the formula, I would know this needs to be 9b to the 4th with a plus. And then here you might want to use the formula, but it's just these two multiplied together. So you get minus 3ab squared. An idea from grade 11. Do you remember in grade 11 you were not allowed to have square roots on the bottom of fractions? So in grade 11 you had stuff like 5 over the square root of 3, and this you would lose a half a mark because it wasn't simplified. And you would have to get rid of the square root on the bottom by multiplying the top and bottom by square root of 3. And in mathematics, then this is considered simplified. Historically, why is that? Well, if you had to do this by hand, which existed at one time, this would probably take you to get 3 decimal places, 10 to 15 minutes. And if you did techniques with this one, it would take you an hour and a half. So the simplified version is better because it takes you 10 to 15 minutes instead of an hour and a half. Okay? It's a little obsolete now because if you wanted to get this as a decimal, what do you think you could do? And how long would it take you? calculator and it'd take you like a second. And then you would say, well, this one would take me longer because first I would have to do this, and now I'm typing more things into my calculator, so this is going to take me 5 seconds. So maybe the first one is better in today's world. But historically, there has been a development of what it means for something to be simplified in mathematics. And one of the rules was that you shouldn't have square roots on the bottom. Even though, for this example, we could now say that's obsolete. Because either you want the answer is exact, then the 5 over root 3 is exact. Or you want it as a decimal, well then I need to use my calculator. It doesn't make sense. If we have a technological tool that makes it faster, why should we do it a longer way? Okay? However, it's still, I think, in the curriculum because you also learn questions that look like this. 5 over 2 minus root 3. And you had to get rid of that square root on the bottom. And now you're going to see, does your memory tell you how to do this one? No. So again, what I'll try to do is I'll try when I reteach you something to reteach it with the reasoning why, because if you know the reasoning why, your chances of remembering it are better. Now the hard thing about mathematics is when we usually learn new math, understanding the reasoning why is often just beyond our mental grasp at that moment. And so even though a teacher shows you probably why it happened, it's like, I don't get it. You're in that mode at that time. And you can't remember it, but you spend time learning how to do it, and then you get it, and then you have like, oh, I can do it if I know the steps, but I don't know why. And then later, if you see that same thing, it might be, now it makes sense. So hopefully that happens a number of times here. Now the steps you would have been taught is a fancy math word, and says you should multiply by the conjugate. And the conjugate is a nice math word that is so confusing that it's easy to forget, and that's probably why you forget it. But the conjugate in math is the same binomial, but instead of a minus sign, a plus sign. And if you multiply the bottom by that, you also have to multiply the top by this. And you would distribute things out, and on the top, well, for now, I'm just going to, on the top, I'm going to multiply 10 plus 5 root 3. Because I would distribute. And on the bottom, if you multiplied it out, you would have to distribute, use all your arrows, because it's 2 things times 2 things. So the 2 times 2, that will be 4. And maybe you start to notice, hey, this is a difference of squares. So when I multiply the 2 times the root 3 and the minus root 3 times 2, those will cancel out completely. And then I'm just going to be left with minus and root 3 times root 3 is just 3. And we've gotten rid of the square root on the bottom. And the reasoning behind it is because your difference of squares, which I have written up there as well, right? Squaring a square root gets rid of it. They're opposite of each other. So as soon as I write x plus something, x minus something, that's a difference of squares, and the difference of squares answer squares whatever you had to begin with, which means any square roots you had to begin with are now whole numbers again. And that's the reasoning why. So if that makes sense, you might remember, oh, the word conjugate's hard to remember, but I know that I need to multiply by something to get that difference of squares, so my square roots cancel out. And once again, in our day and age, you don't need to do this because you can type it into your calculator. However, this is going to be a strategy we need in limits. And sometimes, this is called rationalizing the denominator because you make the denominator from an irrational number to a rational number. And that's why the name is called rationalizing the denominator. But we're going to sometimes have to rationalize a numerator. And we're going to use this strategy in limits. So there is a reason that they still have that in grade 11, even though for simplification purposes, it's obsolete, because we can use our calculator to get an answer. But for calculus purposes, this was important. So we're going to rationalize the denominator of this one. Well, I need to make that difference of squares on the bottom because I want to get rid of the square root. So this would need to have a plus sign. And I can always tell in my grade 11 students which ones are just trying to memorize the steps and don't understand what's happening, because they will often put the minus sign twice. And like, that doesn't make a difference of squares. So then you're not understanding what's happening. Now here, on the top, you would get 2. You distribute, right? Because this is in brackets, this is in brackets. And on the bottom, now, when this is squared, it would just be x plus 3. And minus 2 times minus 2 will be minus 4. There's your difference of squares. Would you like, is it helpful to put this in the square root and square it? So you can really see the difference of squares? Because that's what's happening, right? We have this one squared minus this one squared. And of course, we can now simplify this. X plus 3 minus 4 will be x minus 1. And it's okay to leave it simplified like this. It's also okay to leave it simplified in a factor form. And can you see that the top has a common factor of 2? And sometimes if you want to leave it in the simplified factored form, and our whole purpose was to rationalize the bottom, I might not even have multiplied out the top. Can you see that when I refactored it, I just got what I started with at the top? Just a 2 times this. So you can sometimes leave things factored, because if you're going to simplify something, the factored form will be what helps you simplify it the most. The bottom we wanted to multiply out because that was our purpose. Our purpose was to get rid of those square roots. So that made sense to multiply that up. Okay, I'm going to let you try this one. And then multiplied by, oops. multiply by the right thing. I left it factored there at this time. The bottom, when it gets squared, this one squared just becomes x minus 2. Sometimes I might keep that in brackets temporarily. Minus x. It would be good if the x minus 2 was second. Then it would be important that you had the brackets there because you are subtracting. Subtracting causes all sorts of arithmetic errors. And then when we combine our like terms, we just get a minus 2 on the bottom. I left the top factored. Now, something you have never done before is rationalizing a numerator. This goes against simplification rules. Because if you rationalize the numerator here, then you'll have a square root on the bottom, which seems like kind of counterintuitive. Now, this is an exciting question because it's really connected to what we're going to be doing with limits. For example, in this one, can you see that there's a non-permissible value of 16? So this will be the type of question, if you have a non-permissible value, something that's not allowed, limits is kind of like math's way of saying, well, if that's not allowed, let's try to do as close as possible, because if we get in trouble by plugging in 16, let's see what happens when we plug in 15.99. And let's get close to it and see what it's equal to. Because right now, if you plug in 16, you're going to divide by 0. If you plug 16 on the top, you're going to get 0 on the top. And then the question is, well, what's 0 divided by 0? Well, you can't divide by 0, and 0 divided by 0. This seems weird. Okay? But let's rationalize. And if I was rationalizing the numerator, I need my difference of squares. And once again, my purpose was rationalizing the numerator. I'm going to leave my denominator factored. Whew. Okay, this is one of those moments where I'm like, this is going to be exciting, guys. This is a terribly exciting question. Because on the top, when you rationalize, okay, difference of squares, square root of x, that'll just be x. Minus 4 times plus 4, that'll be minus 16. And we have a factor that's the same. So that's the nice thing about not multiplying out the bottom, that we notice that if this is the same as this, and these simplify, we are now left with, and careful with this, because this is typical of my grade 11s. They're like, oh, it's simplified. I'm just left with this. Well, this is still on the bottom, right? This is still on the bottom. The 1 is on the top. Okay? Now, I'm going to ask you. We wanted to play around with things that weren't allowed. 16 wasn't allowed. 16 would cause you to divide by 0. So limits say, well, play around with it. Try doing something close to 16. Try doing 15.99. Now, the problem with 15.99 is, how's your mental math? What's the square root of 15.99 to 7 decimal places? I'm kidding. But your mental math wouldn't be very good, right? No, that's not expected. Do the square root of 15.99 to 7 decimal places with mental math. But would you agree, since we just multiplied by 1, what we're doing here is we're playing around with what something looks like. And sometimes in math, like a half, you're like, no, I don't like a half, I like 3/6. They're the same, just look different. Would you agree that what we've done is created something the same that just looks different? And the crazy thing about the thing that's the same that looks different is we weren't allowed to play around with 16 before. But now we can. What happens if I plug 16 into this now? I can do this. Square root of 16, is that better than square root of 15.99? Yeah, that's perfect, right? I'm going to get 1/8. When x is 16, this equals 1/8. So what we're going to find in calculus is going to ask us in limits, and it's going to look like this. What is the limit as x gets close to 16 for this? And you're going to say, I'm not allowed to put 16 in. In fact, I get 0 on the top and 0 on the bottom. But it's equal to 1/8. Thinking back to the units you've done in grade 12 pre-calculus, if this was a graph, y equals. We wouldn't know, we never graphed. This is kind of like a mix of a rational graph and a square root graph combined. Okay, so we've never graphed this. However, in grade 12, what did you do when you had a factor that canceled out? When you had a non-permissible value, x can't equal 16, but you were able to cancel out. You got a hole in your graph or a point of discontinuity. So your graph looks something like this. Had a hole. And that hole would have an x coordinate of 16, because that was the non-permissible value that canceled out. And to find the y coordinate of that hole, you would take your new equation and plug in 16, and you would get 1/8. And this is what a limit is looking for. A limit is saying, well, I'm not allowed to put in 16, but as I get close to 16 from this side and get close to 16 from this side, do I get close to a certain y value? Sometimes the answer is yes. Whenever a graph had a hole, the answer would be yes. It gets close to that hole, even though that's not part of the graph. Sometimes our non-permissible values were asymptotes. In those cases, your limit does not exist. Or sometimes we're going to say, if the graph always went up forever, we're going to say the limit is infinity, because it just keeps going up forever. So we're going to make connections between some of those concepts in grade 12 and what we're doing in calculus. Okay, I have 2 more for you to try, including one with a complex fraction. That sounds difficult, right? A complex fraction is when you have a fraction, and inside that fraction, you have fractions. So do you see we have a fraction inside of a fraction? You dealt with complex fractions a lot in trig identities when you had to do proofs. You learned strategies to simplify them so that you didn't have a complex fraction in the end. So we're going to do that with C, but first I'd like you to try B on your own. So, such beautiful math happening. So that's what we'd have to multiply by. Again, it's just the idea of a difference of squares. So you need the same thing, one adding, one subtracting. Then when you multiply it out, the bottom I would leave factored, and the top gives us x cubed minus 1. Boy, that sure reminds me of something we did earlier today. That's a difference of cubes, because x is cubed, 1 is a cube. So you could factor the top to be, and this is probably what you probably stopped at the x cubed minus 1. You're like, I did what was asked. Like technically, you are technically done at this point, because the question said rationalize the numerator. Yeah. But some fun stuff appeared. We have that difference of cubes on the top, and when I factor it, oh my, The x minus 1's cancel out. And we get this. Which means that this original graph would have had a hole at 1 comma. And if we want to find the y coordinate of the hole, we now see, can I plug it into the new equation? Is 1 allowed? Yes. I would get on the top 1 plus 1 plus 1. Love that math. 3. And on the bottom, I would get 1 times 1 plus 1, 2. And so we're going to learn that the limit as x goes to 1 in this original equation, okay? This is how the limit question looks in grade 12 or university calc. Okay? They're going to ask that question. What happens when x gets close to 1 of this equation? We can't plug in 1 though, because it's not allowed. But we learn some algebra techniques to see that it works. Do you want to know a quick shortcut to tell if there's a hole? In this equation, the non-permissible value is 1. If you plug 1 into the bottom, it's a non-permissible value because you get 0 on the bottom, and that's not allowed. When you plug 1 into the top, you get 0 on the top. And so if you get 0 divided by 0 ever in an equation, you will have a hole. Notice in the last one, when we plugged in 16, we got 0 on the bottom, but we'd also get 0 on the top. And in this case, 0 divided by 0 was 1/8. In the example that we just did, 0 divided by 0 was 3/2. So 0 divided by 0 appears to show up as many different numbers in many different places, because it's not possible mathematically. But when you get close to the value, you will get close to the hole. And that is one of the big ideas of limits. So let's do the last one together with the complex fraction. First of all, we have a square root on the top. And if you wanted to multiply by the conjugate, that's what it would be. Perfectly fine. And that will get rid of your square root on the top. I'm going to leave it back on the bottom, but I'm going to get 1 over x minus mathematically, if you have fractions on the top and fractions on the bottom, one of the strategies that you can use to get rid of fractions on the top and the bottom is to see if you could combine things to be a single fraction in your numerator and a single fraction in your denominator. Then a fraction divided by a fraction you can multiply by the reciprocal, and you will be safe with no fractions inside a fraction. So if we did that in this case, okay, can you see that here I can multiply this by x over x, and here I might multiply this by root x over root x, so that I can get a single fraction in different places? On the top, I would get 1 minus x all over x. I like to use a big, long line. Sometimes I even make it thicker for my main division lines. On the bottom, can you see that if you got a common denominator here, you would get a root x? I'll do it in 2 steps. I was going to do it all in 1 step, but I'm going to rewrite this x minus 1 as x minus 1 over 1. And in the brackets, I'm going to add those together by getting 1 plus root x over root x. close that bracket. And now I have a fraction over a fraction. If you have a fraction over a fraction, you can, dividing fraction rules, multiply by the reciprocal. So I'm going to get 1 minus x over x multiplied by this one. Can you visualize this as one fraction where on the bottom you just have root x? On the top, I'm going to leave it as these two factors. I'm not going to multiply it out. Again, sometimes in math we can save time by not multiplying something out because it's nice to have the factors. So when I flip the bottom, I would now have root x on the top, and I would have x minus 1 and 1 plus root x on the bottom. Oh, this is, I'm sorry, there's way too much exciting math. Like, I should have toned down my examples, but this, again, taps on something. You've seen it before, but sometimes you forget it. Okay? On the bottom, I have three factors. This, and this. On the top, I technically have two factors. I do have a single fraction. It's no longer a complex fraction. That's wonderful. But there's something that can simplify that sometimes we forget to see. Okay? We can only simplify a factor if it's identical, and none of them are identical. You are not allowed. Oh, you are tempted? Math? Like, math is tempting. It tempts you to do stuff you're not allowed to do all the time. You will be tempted, oh, can I cancel out that square root of x? No. You can only cancel out a factor if it's identical, right? You cannot cancel this out because this is connected to the plus 1. This makes this one whole factor. And the only way I could cancel out this 1 plus root x is if I had an identical 1 plus root x on the top. But these two are not identical. One is 1 minus x and one is 1 plus x. However, you have seen this before. You may have forgotten it, but you can take 1 minus x and factor out a negative 1, which would, in a sense, if you take out a negative, that would make the x positive and the 1 negative. So that would make it x minus 1. Beautiful. Which means if I do that, now I have all the factors listed. And this graph has a hole in it, and this graph has a limit that exists. And we needed all of those algebra skills in order to figure it out. Because now I would be allowed to plug in 1. On the top, I'd get negative 1. On the bottom, I would get 2. And this limit would equal negative 1/2. But there was a lot of algebra skills that we needed to remember from previous years just to get there. So all of those skills that we've been developing in the past, they come back and help us here. Okay, so that's where we're going to stop. I'm going to give you a worksheet and questions out of your textbook. You do not have to do them all. Normally, like, the worksheet would be more than enough. The textbook would be more than enough. But take a look at the questions and try to find, there's some challenging ones. Ideally, I would love if you did every single math question I give you, because I know that the more practice you do, the better. But at the same time, you also have to realize you're busy and you have time. And sometimes doing math of questions you know how to do is not really useful. Like, if I give you a whole bunch of, we're going to add single-digit numbers. We're going to add 2 plus 3, 2 plus 7, 9 plus 6. Some harder ones, because we have 15 up there. But you know how to do that already. So try to find, when you have the homework, and when we're finding the homework, these are the ones out of the textbook, and I'll give you the worksheet as well.